Thanks for tuning in to this Fidus Systems video. Today we're going to discuss the FSF AD-15000A. In the remainder of the video, I'll simply refer to this product as the 5000A. The 5000A is a 5 gigasample per second, 12-bit A-to-D card in a double-wide VIDA 57.1 compliant FMC footprint. It mates with the Xilinx VC707 carrier card and receives all DC power from the 707. The card interleaves a pair of analog devices, AD9625 converters. Each of these parts is sourced from a 2.5 gigahertz low jitter clock source. This clock source features less than 50 femtoseconds of jitter in a 1 kilohertz to 100 megahertz bandwidth, or less than 20 femtoseconds RMS of jitter over 10 kilohertz to 100 megahertz bandwidth. The input signal bandwidth extends from 500 kilohertz to 2.8 gigahertz, and DC power for the card is less than 16 watts. Performance for the card is typically within 1 dB of the performance of each individual AD9625. There's also provision for external clock and external trigger. Here's a photo of the card where you can see the external trigger, external signal input, and external clock input. The onboard low jitter clock source is shown here. A wideband, well-matched split network is here. It splits the signal into the AD9625 devices, and the clock phase splitting network is here, and it also allows the phase of the clock's split to be adjusted. A low noise power section is also on board. This is the Xilinx VC707 carrier card. You can see the FMC connectors up top here that the 5000A plugs onto. Also required is the Xilinx Vivado design tool at version 2014.1, and the Xilinx JESD 204 IP is also used at version 5.2. Let's have a quick look at the architecture of the 5000A. So as mentioned, there's a precise split of the input to the two A-to-D converters, broadband and well matched. There's fine control of a differential clock phase that's applied to the two converters from either the onboard low jitter source or an external clock. There's an ADCLK part from analog devices used to split the sysref signal, primarily used because of the low skew offered by the output pair. The system runs with a sysref for deterministic latency or JESD 204B subclass 1 operation. Each A-to-D converter has 8 lanes feeding the FMC connector. Each of the lanes runs at 6.25 gigabits per second for a total of 50 gigabits per second from each converter, or 100 gigabits per second in total through the FMC connector to the VC707. The clock phase split network is adjusted through an analog device's AD5662 D-Day converter. And this just summarizes what we've discussed with the architecture. The AD9625 device itself is a 12-bit part, as we mentioned. There's a 2.5 gigasample per second speed grade available. Bandwidth is at 3.2 gigahertz and power 3.9 watts. Aperture jitter is kept low at 80 femtoseconds so that high frequency or high slew rate signals are faithfully digitized. For a 1.8 gigahertz input case, the data sheet gives us for spurious-free dynamic range, a 77 dB figure. Signal to noise and distortion at 55.9 dB for an effective number of bits equal to 9. And a signal to noise ratio typically at 57 dB. That's for a sine wave at 1 dB below full scale. The part also features digital down conversion and decimation filtering, but we won't discuss those in this presentation. So the 5008 interleaves a pair of 809625 devices. Ideally, interleaving would provide a perfect clock split of 180 degrees to each converter. Each converter would be presented identical input signal levels, identical input frequency response. The full scale of each converter would be the same. The aperture delay would be the same, and the DC offsets would match. In this case, if you take alternating samples from each of the two A-to-Ds, you'll end up with a stream at 2 times the individual rate. And with perfect matching of gain and phase and clock, DC offset, any unwanted interleaving spur energy will perfectly cancel. Of course, real world isn't perfect, but let's have a look at what a perfect cancellation can look like. The blue trace represents frequency domain and time domain from one converter. The red trace, frequency domain and time domain from the second converter. The black is the interleave combination of the two. In this case, we have a wanted low frequency input. That's shown at the output as well. Each of the slower sample rate streams shows the expected sampling products on either side of the sampling frequency. Here would be representing 2.5 gigasamples per second. In the higher frequency domain, these have perfectly canceled out. And this is the 5 gigahertz end of the interleave stream. If we were to purposely mismatch the gain and take a look at what happens, we can see now the interleave stream shows some energy in the midband on either side of the 2.5 gigasample per second clock rate of the individual converters, because there's been imperfect cancellation. You can see that in the time domain interleave stream as well. So we've seen real world interleaving will have to deal with things like gain error and all sorts of aperture delay errors between the converters, DC offset errors. Any of these things that aren't compensated will lead to spur products from the interleaving process. You have to keep tight control of the levels. If you have level differences into the A-to-D converters on the order of 0.002 to 0.003 dB, or phase differences on the order of 0.015, 0.01 degrees, you'll be outside of this contour. Inside, your interleaving energy is below your spur-free dynamic range of the part. Outside, it exceeds the spur-free dynamic range. So tight level and phase control are definitely required. We cancel the gain differences in the digital domain, and we cancel phase differences by adjusting the clock phase applied to each of the A-to-D converters. This can compensate for any delay differences introduced in the signal splitting, any aperture delay differences between the converters, and any phase differences introduced by the actual clock phase splitting network itself. We also offer offset correction, and there's 2 different options available for that. One where offsets are canceled in both converters, and one where the offset from one ADC is made equal to the offset from the other. This can be useful if the input network was to be modified so that DC content was passed to the A to D converters. So what happens if we put in an input signal and allow the gain to be uncompensated? Here we have a 1.9 gigahertz signal. It consists of 60 megahertz of bandpass noise. This is an interleaved stream with gain error uncompensated. This is an unwanted interleave product. If we turn on all correction, we can see the unwanted product has been pushed into the A to D noise floor, and we're left with just the wanted input. Let's look at the 1.8 gigahertz sine wave case mentioned in the AD9625 datasheet. The datasheet says this signal to noise and distortion could be expected to be about 55.9 dB. This is a single ADC on the 5000A card, and we can see we're seeing SINAD values very close to the datasheet values. The 1.8 gigahertz in this case has aliased down to 700 megahertz because we're looking at a 2.5 gigahertz sample rate. If we now look at a 5 gigahertz sample rate and an interleaved output, the 1.8 gigahertz input is now where you would expect it to be. No aliasing has occurred. And the previous location of the 700 megahertz alias product is shown here, suppressed by about 78 dBc below the wanted. The 5000A comes with evaluation bit file, register configuration file, and fully active cancellation IP. ChipScope output is used to demonstrate a waveform capture, and this output is also given in a power spectrum view so that the power in the input can be viewed. Let's look at the next slide. It'll give you a better idea. So here's a ILA or ChipScope capture provided in the evaluation platform, the time domain in the top trace and the frequency domain power spectrum in the bottom. The marker has been placed at the peak of the power spectrum, and it shows the scale here and the frequency here. From these values you can calculate the actual frequency, and the scale here on the level is actually the you divide this by 100 to get the actual value of the input relative to full scale. So this represents 96 divided by 100, or minus 0.96 dB full scale. So in summary, the 5000A card has combined a pair of 2.5 gigasample per second ADCs, a very low jitter onboard clock source, and interleaving IP that can suppress unwanted interleaving artifacts. Customization of the system is available through Fidus Systems. If you'd like more information, contact us at fidus.com. Thanks for watching this video.